Firstly, we give the introduction and the background. Secondly, I introduce a new lifelong hybrid learning model for the lifelong learning, which is called the lifelong Fei Ye. Thirdly, I present the theoretical analysis for the forgotten behavior of the models. And then I introduce a new dynamic expansion approach for the lifelong learning. Finally, I give the conclusion and the future work. What is lifelong learning? Sometimes lifelong learning is also called continual learning. Continual learning defines a process capable of continually acquiring the new skills without forgetting previous learned knowledge. So the lifelong learning is more like human beings who can continually learn the new skill and knowledge without forgetting. So they have two aspects for training the lifelong learning models. Firstly, to be an artificial intelligence system, it should be continually learn the novel data set without forgetting. Secondly, once the model has been trained on the past data samples, the model should use the prior knowledge to accelerate the future task learning. However, most of methods are focused on the first one. So the main challenge of lifelong learning is the network of forgetting. For instance, if we have learned a sequence of n tasks, and the model is trained on the initial task, when the model learns a novel task, the model would lose information on the past sample. If the new task is an entirely different database. I introduce the two common settings for the lifelong learning. The first setting is a class incremental setting. This means that each task is defined as one of several incremental class, and the model learn a sequence of tasks. This means that the model would learn the novel classes or would learn the image from the novel classes. And for the second setting is a dataset incremental setting. This means that each task is defined as an independent dataset. The second setting is more challenging. So my research work is mainly focused on the second setting. Before I introduce my method, I firstly introduce several technology which I used in my method. Firstly, I shortly describe the learning procedure of the generative adversarial net, the GAN. The GAN usually includes the two components. The first component is the generator, and the second component is the discriminator. The generator take a random noise vector draw from a normal distribution as input and output fake images. And the discriminator receives a fake image and also the real image and output the prediction. The learning procedure of the GAN aims to encourage the discriminator to distinguish between the fake image and the real ones. On the other hand, the generator is encouraged to learn to output the image, fake image, which are very similar to the real one. For the second model, which is a variational autoencoder, Fei Ye is also one of the most popular generative models, which consists of two components, the encoder and the decoder. The encoder is usually the Gaussian encoder, which take the input, which take an image as input and output the hyperparameter of the Gaussian distribution, and the code is drawn from this distribution, and then the decoder receive this code and output the reconstruction. And the VE is trained by maximize the data likelihood. And then I introduce how to overcome forgetting by using the generator. So this approach is called generative replay mechanism. GRM usually includes the two components, the generator and the classifier. For instance, the GRM is trained on is finished at the first task learning, and then at the second task learning, we use generator to generate the images, and also we use a classifier to make a postal label for the generated images, and then we incorporate the real sample from the second task and also the generated image into the joined dataset. So the model is actually trained on the joined dataset at the second task learning. So in this way, this can avoid forgetting because the joined dataset has already contained the information about the first task. However, existing GRM approach has two main drawbacks. Firstly, GRM only performs the classification and the generation task. Secondly, GRM does not learn the meaningful latent representation due to lack of an inference mechanism. So in order to address the above problem, in this representation, I introduce a new lifelong learning setting, which is called lifelong generative modeling, which is fully unsupervised, and there have no class labels. So this setting aims to learn a model which can map the image from a sequence of tasks into a single latent space. So this learning setting has two benefits. Firstly, we can discover meaningful latent representation across domain, and we can also model the correlation between the different domains into the latent space. Secondly, we can record the data from the latent space. So in order to address this learning setting, I introduce a new model, which is called lifelong VE gang, which lifelong VE gang is able to learn the latent representation across domain under the lifelong learning. So in order to provide the inference mechanism for the GRMs, lifelong VE gang introduced two additional inference network. The first inference network is used to model the conditional distribution. This conditional distribution output the two variables C and Z. C is a discrete variable which aims to capture the discrete variation of the image, such as the class label, and Z is a continual variable which aims to capture the continual variation of the image. And we also introduce another inference model, which models the conditional distribution, and this conditional distribution take Z as input and output the domain variable A. So this conditional distribution arm to capture the task information from the learning setting. And in order to reduce the gradient variance, we introduce Gamble softmax to the sampling of the discrete variable a. And in the final, we incorporate 3 variables into the generator, and the generator can give the reconstructions. So in order to train the whole model, we introduce to use the variational autoencoder loss, which includes the 4 terms. In the right-hand side, the first term is the negative reconstruction error term, and other term are care divergence term, which are used to regularize the conditional distribution. Additionally, because we also use the adversary loss to train the generator only, in order to generate the past data sample. So for the detail of learning procedure, which are very similar to the GIM. Firstly, for instance, the lifelong VE-GAN is finished at the first task learning, and then at the second task learning, we use the generator to generate the image, and we also use to train the inference network to give the postal variable for the generated images, and then we incorporate the real sample from the second task and also the generated image into a joint data set. So in this way, the lifelong VE-GAN can overcome the forgetting. However, because this process would require a huge memory requirement, so in order to reduce the use of memory, we introduce use a small buffer to preserve the previously learned generator parameters after each task switch. So then in the next task learning, this buffer is used to generate a batch of images from the stoned model. So in this way, this can reduce the huge memory requirement because we just preserve the generator parameters into a small buffer. So for the result, we train the lifelong VE-GAN under the learning of syllaba to the CACD. Syllaba and CACD are 2 different human face data sets, and we give the generation and the reconstruction. And also we train our model under the 2 different database, the syllaba and the 3D chart. So those results can see that the generator in the lifelong VE-GAN can generate the image from the 2 different domains, like a 3D chart and human face. And also our inference model can infer the accurate variable latent representations, which can allow the generator to give the better high quality reconstruction result. Additionally, in order to evaluate the quality of the learned representations, we perform the image interpolation experiments. Firstly, we select the 2 different images, the human face and the 3D chart, and we use the inference model to infer the latent representation for the human face, Z1 and A1, and we also use inference model to infer the 3D chart, Z2 and A2. and then we make the interpolation on the latent space. And finally, we take the Z and A to the decoder, and the decoder will give the reconstructions. So in the following, I report the interpolation results. So we can see that when we make interpolation on the latent space, one image can be transformed into another image. So this shows that our model can learn a small latent space, which can preserve the information from the all task. In addition, I also explore the disentangled representation learning for the lifelong learning. So we introduce to penalize the KR divergence in the objective function in order to induce the disentangled representations. And this model is trained under the learning of human face and 3D chart dataset. So we can see that the model can discover several disentangled representation, such as gender, pose, and the skin variance. And in order to evaluate the quality of the reconstruction of the model, we use the reconstruction error classification accuracy, evaluate on the reconstructed image, FID and IS score for the evaluating the performance of the model under the lifelong learning. So it shows that our model outperform other baseline in every task learning. Additionally, although our model is mainly focused on the unsupervised learning, we can upgrade our model to the supervised learning because our model can capture the discrete variance of the image, such as the class label. So in this way, we train our model under the Mechnism fashion and also the Mechnism to SV HN dataset. So the result shows that the model can achieve the promising result on the supervised learning task. Additionally, to be our best knowledge, this paper is the first work to explore the semi-supervised classification under the lifelong learning. So for this result, we can see that our model outperform the baseline lifelong GAN, and also our model can achieve the results which are very similar to which are the gap between the result from the baseline that does not trend under the lifelong learning is very small. So in the next, however, the theoretical analysis for the forgotten behavior of the model is less studied. In this representation, we studied the forgotten behavior by answer the two questions: what factor causes the network forgetting, and how to explain the forgotten behavior of a model. In order to answer those two questions, we provide the insight for the theoretical framework. The main insight is that we formulate the forgotten behavior as the variance of the model's risk. So as shown in this picture, there have the source risk. Source risk means that the risk is the risk of the model is evaluated on the generated data set. The target risk means that the model's risk is evaluated on the testing samples. And we also have the concept of the accumulated errors. The accumulated error usually is generated by the model across the multiple GIM process. So as shown in this figure, the small source risk cannot guarantee a small target risk because they have the accumulated error terms. So in this work, we drive the risk bound for a single model at the certain task length. For this risk bound, the left hand side is the target risk, and the first term in the right hand side is the source risk, and the last term in the right hand side is the accumulated errors. We measure the accumulated error by using the discrepancy distance. This means that a discrepancy distance between the generated image and the testing samples. So if the generated image is far away from the testing samples, the discrepancy distance is very large. So this can lead to accumulated errors. Because we measure the risk for a certain task, so as the number of tasks is growing, the accumulated error will be also grows. So this can explain why the model forgetting more when learning a growing number of tasks. So due to the drawback of the single model, we also provide the risk bound for the dynamic expansions, and we divided the risk bound we divided the right hand side into two parts. The first part is the risk for the components that are trained only once. So this means that there have no forgetting for those components. For the second part, we evaluate the risk for the components that are trained more than once. So this means that a certain component is reused for learning a new task. So there have some forgetting happens because we use the generative replay mechanism to generate the image, which cannot represent the true underlying data distributions. And from this risk bound, we can find that the number of components in a mixture model can trade off between the model's complexity and the performance. For instance, if the number of components is equal to 1, so this means that we have only the second part. We have only the second part, so there have more accumulated error terms, and the target risk should be also very high. So if the number of components is equal to the number of tasks, this means that there have the right hand side is only the risk for the components that are trained only once, and in this case, there have no forgettings. So inspired by the theoretical analysis, we introduce a new dynamic expansion model, which can satisfy two aspects. Firstly, when seeing an entire different task, we need to build the new component to learn this task in order to avoid the forgetting. Secondly, in order to reduce the model's parameters, we introduce a knowledge measure approach that compares the knowledge stored in the previous learned components and the incoming task. This knowledge major approach aims to evaluate the novelty of the incoming task, and which is used for the expansion and the selection of the model. So in the next, I describe how to calculate the knowledge major. So we assume that we have already trained two components. Finish two components at the first and the second task lane. So we use because each component is a variational autoencoder. So we can use each component to generate the knowledge, generate the image, which can be seen as the knowledge, and also we can draw a group of samples from the new task, the third task, which is the new knowledge. Then we use a variational autoencoder loss to calculate the loss value. For instance, we use the first component to calculate the knowledge generated by itself, and also we use the first component to calculate the loss value for the image from the third task, resulting in the K2, and then we calculate the absolutely difference between the K1 and K2, resulting in the K3, and the K3 is the knowledge major between the knowledge generated by the first component and the knowledge from the new task. So we can also do the same for the second component, resulting in the S3. And then we introduce two user criteria to evaluate the novelty. For instance, if the minimized knowledge major is larger than the threshold, this means that the new task is novel to the already learned knowledge stored in the component. So in this way, we need to build the new component. Otherwise, if the minimized knowledge major is smaller than the threshold, and we should select the corresponding component to learn this new task. So for the detail of network structure, in order to further reduce the parameters, we actually share the parameter between on the inference process and also the decoding process. So the new component is built based on the shared encoder and also the shared decoder. And during the learning, in order to avoid the forgetting, we just optimize the current component parameters. In addition, because each component has an independent latent space, so we cannot learn a single latent space for the multiple task. So in this way, we introduce to learn a student network within the mixture model. So we consider the mixture model as a teacher network, and we introduce the student encoder, which is built based on the shared encoder, and we also build the student decoder, which is based on the shared decoder. So for each task learning, the student can update its parameter and to receive the information from each component. So for the detail, for instance, we can use each component to generate the knowledge x1, x2, and xk, and the student receives the knowledge is trained on those knowledge by using the knowledge distillation laws. So in this way, the student can accumulate the all knowledge from the component into a single latent space. So for the results, we train our model under the five different tasks. Each task is defined as an independent data set. And after lifelong learning, we can give the reconstruction from the teacher model. So we can see that each component can capture the each component can capture a similar domain, our single domain, and also can give the accurate reconstructions. We also show the result from the teacher model because from student model, because student model is able to accumulate the knowledge from the multiple component. So, but this result is not good than the teacher model because this is usually the generated image from the teacher cannot represent the true underlying data distribution. So the student only receives the generated image as the knowledge. So we also train our model under the complicated data set, which includes the human face and the nature image, and also the 3D chart. This result shows that our student model still can give the reconstruction for the complicated data set. In order to evaluate the smoothly of the latent space of the students, we make the image interpolation experiments. And we firstly make interpolation on the latent space, so we can see that the human face can be transformed into a 3D chart. In addition, we can apply our model to the image-to-image translation task. This task is more challenging because we need to learn a pair of image for each task. After lifelong learning, our model can also give the a very good reconstruction results for the image-to-image translation task. And also, our model can also be used for the supervised learning task, especially for learning a long sequence of database. For instance, we train our model under the 6 different database. So this result shows that our model outperforms other baselines. In addition to the dataset incremental learning setting, we also use our model for more general continuous learning dataset, the class incremental setting. And those results show that our model can be also used for the more general continuous learning setting. In the next, I would like to provide the result for the theoretical analysis. As shown in the red pictures, we train our model. We train a single variational autoencoder with the generative replay mechanism, which are used to overcome forgetting. So this model is trained under the 3 tasks. and we measure the discrepancy distance, the source risk, and also target risk. And this result shows that usually we can keep we can get the small source risk because the model can access the sample from the source domain. And we can also observe that the discrepancy distance is growing because the GIM used in the model can change the image, which cannot represent the true underlying data distribution, and the accumulated error will be generated by each run of the GIMs. And also we can see that the target risk is also increased when learning a more task. In the next, we evaluate the trade-off between the model's complexity and the performance. And we change the different threshold to control the selection and expansion. When the threshold is very large, the model tend to select a single component for learning the 5 tasks. If the threshold is small, the model tend to create the more component to learn the task, and the performance is also corresponding to the number of components. For instance, if we use a single component, the target risk is very high. If we use a more component to learn, the target risk is very small. And also we evaluate the risk of other model during the learning of 5 tasks. And we can see that LGM is a single LGM is a single variational autoencoder to be trained on the generative replay mechanism. So this can say that a single model cannot perform well because they still has a forgotten, and our model can balance the model's complexity and the performance because the risk for our model is kept stable, even though for learning a long sequence of tasks. In the following, we also evaluate the risk of a model when a certain component is reused for learning a new task. For instance, we assume that a certain component has been trained on the minister, and then we use this trained component for learning a new task, like learning the CFA10 and fashion and SVHN. So this means it can observe that when learning the new task, if the new task is very similar to the minister, the target risk is very small. However, in our lifelong mixture model, the knowledge measure is actually measure the similarity between the knowledge already has been learned for the component and the knower and the new task. So our model can also select the reasonable component that can reduce the target risk for learning the new task. Conclusion. We propose a new lifelong VE approach, which can provide the cross-domain latent representation from learning a sequence of tasks. Secondly, we also introduce a new theoretical analysis framework, which provides a new insight into the forgotten behavior of the model. Inspired by the theoretical analysis, we propose a new dynamic expansion approach, which can trade off between the model complexity and the performance. For the future work, there have two directions for our future work. One is called the online continuous learning. Because in our previous work, we focus on the learning setting where the task information is given. However, in a more realistic setting, there have no task label for the data sample. For instance, if we learn a data stream and we can only receive a batch of images for each training step, so this learning setting is more challenging because they have no task information, and the class label is also not provided. So in order to address this learning setting, we need to propose a new approach that is able to detect the data distribution shift during the learning. Secondly, because the image interpolation task is important to evaluate the performance of representation learning under the lifelong learning. However, there have no formal criteria to evaluate the quality of the learned representation under the lifelong learning. So our future work would like to develop the new criteria for the image interpolation. However, this is more challenging because there have no ground truth image for this task. There has no ground truth image for this task. So the one idea for this criteria would be measure the distance between the interpolation result and the original